this is just a talk. And that is, I want to talk about something that we have to know and know better, which is universal or forwarding references. And yeah, because it becomes more and more important. One reason is to deal with views you might need it. So let's jump in. We only have 1 hour. So you all know what references are. If we have an object that exists wherever it comes from, you can create a copy, but you can also create a reference. And a reference means you have a temporary additional name. You can change the object you refer to during the lifetime. And if you then use the reference or the original object, it doesn't matter. So if you modify one, we modify the other. The reference might have additional attributes like being const. That means we cannot use the reference to modify it, but the original object can still be modified. Now I'm using int here. But we can also use auto here. And auto means that the compiler finds out the type. So, and that all is used that when we can use reference to pass objects by reference instead of passing a pointer, which is simulating call by reference in C, we use cast by reference in C++ by either passing objects as a const reference or as a non-const reference. As a const reference, we just want to skip copying. We want to avoid copying. And as a non-const reference, we might want to have changed the argument. So it's an out or in-out parameter in that case. So I think I don't have to tell you the details. You know all that. So one thing that's important to know is, and that is one thing I see not everybody knows that, is that references extend lifetimes of temporary objects. So I can say here, I have a return value, a function getVal returns a string, and by initializing a reference, so here declared as a const reference, I extend the lifetime of the temporary normally at the end of this statement. Otherwise, the return value would be destroyed. But here we extend the lifetime. And to say one thing here is, we only extend the lifetime of what the reference refers to, not anything that is indirectly referred. So we can then use the object without the need to really initialize an object, which might be a move or copy depending on the exact C++ version you use and whether things are optimized away and so on. You cannot bind a reference, a non-const reference, to a temporary object. And oh, that animation is wrong. But that does not compile. But you can do something else. You can use an R-value reference, which we have since move semantics, which means we have something that is about to die. And then, in that case, we can refer to a temporary object. And in that case, this object does not become const, which sometimes is needed, for example, when you use views. And then you can pass it around. Now, we might think, OK, when I use this example, let's switch again from just a direct specified type to auto. And now we have exactly the same behavior. But it's not. It's not exactly the same. Because this is special. This auto with 2 ampersand is special. It is a universal reference or a forwarding reference. And that's important to understand what that is. So coming back to that, we will solve this and look into details over this hour. So coming back to R-value references, we introduced them originally for move semantics. So this is what I usually use to teach to motivate move semantics and why we introduced it. This is a vector on the left. It has pushback, just a pushback member And that was before we introduced move semantics. And on the right, we could push back an object that has a name. We say it's an L value. We could push back a temporary object returned by getData, or just a sum of two strings here, which is also a temporary object returned by an operation. And we could also even push back it even though we don't need it anymore. And in all the latter cases, we did originally copy the objects, but these were unnecessary copies. And it turned out that too much operations are involved, especially with strings, and they allocate memory, so that this code pretty often was not optimized. So you can see, well, the compiler can see it all, but there was too much involved. So we came up with this idea in C++11 to say, well, let's introduce another pushback. And the other pushback is, say, taking an R-value reference, so a new kind of reference, the one with 2 ampersand. You have seen that all now. That was 11 years ago. So, and now the original references are called now L-value references. And now we have different rules that when we pass an object, the compiler looks, is it an object with a name, an L value, or an object that is temporary, an R value, and depending on that, it calls the first or the second pushback. So one pushback if the caller still needs a value, one pushback if the caller no longer needs a value, and the only reason we have to specify something with move is to say, well, hey, compiler, this has a name, yes. You cannot know that I no longer need the value of this object, so move says, in fact, I no longer need this value here. I'm always searching for an acronym for MOVE says this sentence. So if somebody has that, so I could explain it better. So this is not about move semantics. This is about universal references. But we have to clarify things before we start and jump into details. And one thing I also have to clarify is about value categories. So value categories, when I asked in trainings, who knows value categories, nobody raises a hand. If I ask who knows about L values and R values, they all raise a hand and say, oh, that's value categories. So, and let me just ask you in the room, who thinks I have understood what an L value is? That's a trap question, of course. You can only lose. Well, okay, so let me ask a simpler question. What stands the L for? Left. Here's somebody from the committee. L means left. Is not true. Well, it's no longer true. L means locator. Yeah. So what is we have to talk about that. So it all started with Cunningham and Ritchie C. So 50 years ago, we have the 50th birthday of C, and we are still compatible to that. And that's why we have all this mess. No, this feature. Okay. So they wanted to say, when does a statement compile or an expression compile? And it's not enough to say the types have to fit. Because you see it here. The type of I is int. The type of 42 is int. But one of the statement compiles of the assignments and one does not compile. So there must be something more. And instead of writing a long list of 100 things that also have an impact whether something assigns, we say, well, on the left-hand side, there must be an L value. Yes, and there's where the L came from. So L was right. L meant can be on the left-hand side of an assignment. But it was not only for assignments, it was for other things, like, can I take the address? Can I take the address of something? And yes, you can take the address of an L value, but not of 42. So not of an R value, which is the other thing, the thing that can only be on the right-hand side of an assignment. A couple of years later, things got complicated because C, the programming language C, introduced const. So now we have something like this, const in C, and it turned out that you can assign, no, you cannot assign an int, but you can take the address. So when I now formulate the rule, should I say this is an L value, or should I say this is an R value? What is the category of this? And that was the moment where they thought about it and said, okay, wait a minute. Most of the things can still be done, but one of the things that cannot no longer be done is to be on the left-hand side of an assignment. So L no longer meant left. It now means locator value. That's a term written in the C standard. You can see it there. They have no term for the R now. So I don't know. So readable value might be the right thing. So that is what it stands for now. And then we came up with move semantics in C++. We adopted the whole thing. And then we came up with move semantics. And in move semantics, we created an interesting problem. We said, if I have an L value, an object with a name, and I mark it with move, can it be on the left-hand side of an assignment? Can I take the address? So let me just guess. So who thinks that the statement in the middle, std move of s, gets the value hello? Who thinks that this compiles? Okay, I would say 10%. Who thinks that the last statement compiles, though that you can take the address of an object marked with move? Almost nobody. Well, 5%. So here's the answer. Well, if this is a string, if it's an int, then the answer is different. Nothing is easy in C++, you know that. Okay, so there are reasons for this answer. We don't have to explain that here, and I couldn't do that. There are reasons that we wanted to have this behavior. So, and the problem was with that behavior now, what is this? Is this an L value or an R value? If I mark S with move, what is the expression? And the answer was, let's come up with a new name. Let's call it X value, a new category. X for expiring value. And then turned out, but you know, most of the things that apply to X values also apply to R values. So let's do one more move. Let's say, well, X value is a special category of R values, and the former things that were R values are not X values. We'll call them now PR values. Did you understand what I say? No. Somebody says yes, but you knew it all before, huh? Yeah. Okay. So this is what we have now as a rule in C++. We have in any expression in the program, when you compile it, either it is an L value or an X value or an PR value. If it's an L value, it is a locator value. And that means roughly you can deal with the address of the object in the program. It has a location in the program you can use in your code. So examples are everything that has a name, and string literals are L values. So variables, string literals, returned L value references, functions, data members of L values. So then the next category is pure R values. That's everything else we had before move semantics. So, and we called it their R values. They are still R values, but now they have a special category. So any other literal and those objects that don't have a name, temporary objects that don't have a name. And then we have this special category X value, which means usually objects marked with move. And move is just a static cast to an R value reference. So that you can instead do the static cast to an R-value reference, and that is also has also such category. Okay, let's see whether you got all the rules. We have here a declaration on top, a function f overloaded for a non-const L-value reference and a const L-value reference. On the left-hand side, we have a class, and we create a non-const object and a const object of that, and then we try to call the functions also with a temporary object. And what this table shows you, what is possible, so what does compile and which priority it has. So here you see that for v, which is a modifiable L value, it has a name, you can call both functions, but the one with the non-const L value reference is preferred. For c, which is a non-modifiable L value, you cannot pass it to a non-const reference. And you can only bind it to a const reference. And temporary objects have the same roots. Temporary objects, formerly known as R values, now exactly being PR values, they are still R values because that's the precise category, they follow the same rules. Okay, and now when we then extend it to move semantics, we have a couple of new situations. One of them is we can have R value references, so we can declare f to take an R value reference. Okay? And we have a new category that is an object marked with move, which is an X value. And here are the new rules. The new rules say, first of all, an R value reference cannot bind to an L value. You know what? That's why it's called an R value reference, because it refers to R values only. And if it exists, it has the highest priority. If not, there's a fallback, and the fallback is a const L value reference. What you see here is if move semantics is not supported, we switch back to copy semantics. If we have no move constructor, a copy constructor is used, or if we have not overloaded the functions. The other one is taken. So, you know all these. Who has learned already something? Nobody. Who has already learned something here in this talk? Oh, my question was wrong. Good. So I come to the slide where I deeply apologize each and every time I use it. I hope it's not my fault. But it's important to understand that if you don't know that yet. If you have a function taking an R value reference, here for a string, it can only bind to R values. So if you have an L value, an object with a name, and you pass it, you get this famous error message, cannot bind an R value reference to an L value. Yeah, you know what? That's how we build it. We did build it in the rules of the language, and of course then in the compilers. If you pass a string literal, that compiles. Now everybody in this room has to scream. But wait a minute, what is the category of a string literal? No, what is the category of a string literal? L value. So what the hell is this guy in front telling you? Well, you could believe him. You would believe me everything. Huh? That's anyway, because it's C++. It's not because it's me. And no, that's an L value, and it binds to an R value reference. So why? It's a class. There's a hidden operation. Yes, because the type does not fit. So this object is converted to a string. That string is a temporary object, so a PR value, and that is an object that has no name and can be bound to an R value reference. So what you really compile is that. Okay. To pass string, you have to move it. This slide is not over. Let's implement this function. And that's very important. Let's implement this function. We have for s being an R-value reference. What is the value category of s? L value. Yes, it is an object with a name. It's an L value. So the rules of L values apply. And that's funny. That means the function you cannot call yourself. That will not compile. Because you cannot bind an R value reference to an L value when there is no hidden operation converting it to something else. So you have to use move again. And that is the secret hidden details of our rules that move semantics is not passed through. Just when we call this function for an object we mark with move, inside the function it has no move semantics until we mark it with move again. Move also only needs, I no longer need this value here. And here we say, I no longer need this value here. And for those who are asking, why the hell did you do that? If we would say move semantics is passed through, then we couldn't use s twice. Because with the first time, the value would be moved away. Or we would need something like unmove or so. Move is nothing but a static cast to an R-value reference. So that's funny. If you really read this line, we cast s to its own type. But the point is that a static cast does more than changing a type. It has a rule. If you pass to an R-value reference, it converts it to an X value. It changes the category. Okay? And if you understand this slide, and you didn't do that before, you understand a lot more and a lot of the things that go behind the scenes in C++. Okay, good. So let's use this whole stuff. So we have foo, const L value reference. Binds to everything. Good. It's for read-only parameters. We have foo for non-const L value reference. We only bind to non-const named objects. It's an out or in-mount parameter. Then we have foo for an R value reference. It only binds to objects without a name or those marked with move, so to R values, which means to PR values or X values. And that's when we semantically want to steal something, when the caller says, I no longer need the value. There's a fourth category, I don't know if you know that. You can declare a function taking a const R value reference. You can do that, that's allowed. It's a semantic contradiction. Because you say, well, I no longer need the value, but you are not allowed to do anything with my value. Okay. There are easier ways to implement that. That's the first function. But in principle, that's okay. And if you don't use the semantics of C++ we usually apply with this, if you just use the formal language rules, you have a way to say, if something is marked with move and is const, here's an option to deal with it. And what we learned in the standard committee over the past 30 years is there's nothing crazy in the language where we don't find a good use case for. By the way, you have that pretty often. You just need a const object and mark it with move. Then you have such a thing. Which is not a good idea, because then you have disabled move semantics. And because, but pushback we only have is still there for const objects, so we fall back to copying. And for this reason, you could also not use move if you have a const L value reference as an argument. And really nice is you have a function returning a const string. A couple of programmers do that. They say, oh, I have a return value, I don't trust you that you use it useful. I make it const. But that means pushback with get value will no longer benefit from move semantics because you have disabled the move. It will still compile and be a copy. Good. So, wrong topic. We talk about universal references. But I have to make sure that you all know this now. Following from this, we run into a problem. And the problem was, guess we are overloading a function for the main use cases, the main applications, which is give me an object just to read, give me an object so that I can return you something, or give me an object where you no longer need the value. And then let me call that function for a non-const object, const object, or temporary object, or an object marked with move. In C++, very, very often, we don't call functions directly, and not only in C++. That's part of programming, that you indirectly, you pass through arguments somewhere else. And so let's switch to call foo, so which means we call a function, and that function calls foo for us. And how do we have to implement these functions? So from what we just learned, it's clear. These are all L values. Const L value, non-const L value. So we have to make something different, that the last two, the one in the middle should call the one in the middle here, and the last one should call the last one. So we have to do something with that. And the difference is, the first two functions just pass through the X. The last function has to mark it with move again, so that the move semantic is passed through. OK, so we agreed that we don't want, when we write C++ code, each and every time, we just want to pass something through in generic code, and we don't know what we get. Maybe anything, everything. Write 3 functions. And it gets worse. If you have 2 parameters, you need 9 functions, all combinations. And if you have 3 parameters, you can compute it yourself. 27. And that was the point where we came up with, we need something special. And what does confuse every programmer in the world is this something special looks as not being something special. And that's cool. So we came up with a special rule saying we have some special rules for C++ for perfect forwarding. If you have one function taking one argument and you want to pass it perfectly to the right function as if you would have called it directly yourself, then you need 3 things. You need a template parameter. You need to declare an R-value reference of the template parameter, and you need forward. This combination of these 3 things does the right thing. The magic is that this forward becomes a move if what you pass is an R value, so has move semantics. And if what you pass is an L value, it does not move. When we came up with C++ 11, we didn't have a name for that, for this thing. What is X? Oh, it's an R-value reference of a template parameter. And then Scott Myers came out with the term universal reference. Why universal reference? because think about the name pattern of R value reference and L value reference. The name comes from where can it refer to. So an R value reference can only refer to R values. An L value reference can refer to everything, well, depending on whether it's const or not. Good. Unfortunately, the standard committee does not always like what they see. That was, to be fair, a term of the community. Scott was not part of the standard committee. And they came up with a different term, and they called it forwarding reference, which was very confusing for me, because they call X forwarding reference, not X if you apply forward. They call that forwarding reference. It's not forwarding. It's like move does not move. It only marks it as movable. So forwarding reference means you could use it for forwarding, but to do that, you have to use forward. I was, at that time, not as wise as I am now, which means I didn't understand everything I see now. But I didn't feel comfortable with that. We had the discussion, what should I use as term in my books? In our books, the template books. We wrote the second edition of the template book there. And if I would have known what I know now, I would have said, no, I don't switch to forwarding reference. Because the point is, you not only need it for perfect forwarding. That is one use case of what you see here. And yeah. The use case here is you have a universal reference, and with forward, you forward something. OK, but now we have two terms. And you have to be very careful if you see code. If you see code like this, you see a function. And the function has a declaration with 2 ampersand. You have to be very, very carefully look what the thing on the left of the 2 ampersands is. If it's a type, it's an R value reference. And then the rules apply that say you can only pass R values. It only binds to R values. So temporary objects or objects marked with move. L values, you cannot pass L values. So if the thing on the left of the 2 ampersands is a template parameter, then formally this is still an R value reference, but an R value reference to a template parameter. And for that, we have now the special names universal reference or forwarding reference, as you like. And then different rules apply. So you can pass everything, but it's even more. If you have an R value reference, a raw R value reference, you know that the object is not const, which is not the case here on the right. And if you want to forward it to somewhere, here move is enough. On the right-hand side, you need forward. OK. So, no, I skipped that slide. I want to talk a little bit about the details here. So just for fun. So if you read the standard, where can you read this, what I told you right now? Where can you read this? In your book. In my book? In the Move Semantics book. It's written there. It's a little bit tricky to read it in the standard. So what we have here is the following. If you call a function and you have a template and you have an R value reference to a template parameter, then what you pass is something where you have to deduce the template parameter t from. So the compiler has to find out what is t here. So there's a special rule saying that t is not just the type if we have the following situation. If the parameter is an R-value reference to a CV unqualified template parameter. CV unqualified means a template parameter that is neither qualified with const nor with volatile. This case here, well, we have a parameter not qualified with const and volatile, and it's an R-value reference. And if then the argument is an L value, that is the case here, then the type of T is, the type of this is an L value reference to its type. So therefore, T, if you ask T, what is your type, and when you call this function, it's an L value reference to C or const L value reference to a C if you pass an L value. Otherwise, T is just the type. So now, what is the type of X? We deduce T now. With that, we know what the type of T is. Okay, what is the type of X? The type of X is something of this as an R value reference. So T, this type, with 2 ampersands behind. So there, we have other rules in the standard. We call them reference collapsing. So if you have a reference to a reference, what is the resulting type? And the answer is, if you have different kinds of reference, what you get is always an L value reference, except when you bind an R value reference to an R value reference. So when anything is already has 2 ampersands, and now you apply 2 ampersands to it. With that rule, we now know what the type of X is. It is L value reference to C, or to const C, if we pass an L value. And if we pass an R value, it's an R value reference. And that is used then by forward to expand to move. So move is then a conditional propagation, conditional static cast, using also some trick I don't explain now, which says, oh, and then with that information we cast to the forward becomes a move. This is not for ordinary application programmers. This is how we specify. And I could never even come up and think about this. It took me years to learn it. So that means when we come back to this example, if you have the thing on the right here, the T, if you pass an L value, the T is an L value reference. If you pass an R value, it's just the type, and the X is an L value reference or an R value reference. So if you ask what is the type of these things inside, you get these answers. And then we have 2 ways to do that. What you just saw here, we not only use for templates, we also use it for auto. So we said, oh, we need this mechanism not only for templates, we also need it when we have not a parameter, not something that is a template, when we use auto. So this 2 ampersand template parameter is a universal reference, and auto 2 ampersand also is. Coming back to our example, where we said this is special. This is not just an R value reference to a string that is returned. This is a universal reference. And that means the thing on the right can be everything, because that is what was the cool thing why we introduced that. We want to have something that can bind to everything. Universally bind to R values and L values. So that's why universal reference is such a perfect name for that. It was just too universal. That was one argument, because you cannot bind it to I don't, egal, doesn't matter. Okay, good. So let's look at this and with another example. If you write generic code, look only on the left-hand side of this, and you declare something with const auto L value reference, you can initialize it with everything. An L value, an R value, an R value, I mean a temporary object, and PR value or an X value. And the only problem is, with this reference, whatever we bind to it is const. We can no longer modify it from here. When we remove the const here in our generic code, the point is, the thing here on the right could be just a function call, and you don't know what this function call returns. Could return everything. So when we want to keep this perfect, yeah, what do we use? But this makes it const, which is in many cases okay, but there are cases where you don't want to make it const. So if we remove the const, then the problem is a non-const L value reference, whether you write it with a type or with auto, does not bind to an R value. So you cannot use that when the thing on the right gives you back a temporary object. And now here's the answer. The answer is auto with 2 ampersand can bind to everything without making it const. Yeah, it's a universal reference. But we didn't like that term. Okay. Here's one application where we need it. This is the range-based for loop. This is another flavor of the for loop, not the one where we fix the bug. The specification in the standard says, if you have something declared to iterate over a collection, so what we declare here is each element inside the loop. This is equivalent to this code. We take the collection and we iterate over it with an iterator here. So that means we have to call begin and end. But that means we need it twice. We need this object twice. And to have an object twice, you need a name for it. Otherwise, it's not possible. Think about this. We would have here get data, and we would just say this is, we call rg.getData .begin, and then getData.end. We would call getData twice. But what we have to write as code is we call getData, and then we call for the result begin and end. But we don't want to copy anything here. We don't want to initialize a new object. We want to take the return object as it is. So that's why we declare this as a reference, and then call begin and end for it, and then we can iterate over this loop. So if you have that code is compiled. But I wrote here a reference. Most of my trainings, I don't explain what that is. But this talk is about universal references. And guess what? It is one. Because you have just learned what we need here is something where the thing on the right, the thing behind the colon of the range-based for loop can be everything. Everything. So an R value, an L value, const or not const. And it should not make things const. So not const. We have to use a universal reference. That's a perfect application of that. So, what time is it? Okay. There are a couple of things, if you know what I heard, that really create more trouble than what I just told you. So one thing we have is, how do I specify a universal reference to a specific type? Which means the problem with the universal reference is that it's generic. It can bind to any type. But that's not always useful. Sometimes you want to say, this is a function just for strings, but the string might be an R value, might be an L value, might be const, might be not const. So how can we specify that? It's not easy to do that. You have to write something like this. So in C++20, which we have now, you can have a constraint. So we have a template parameter, but this could be everything. So we, in addition, have to say that we require that this template parameter, if we remove constness and referenceness, is a string. But it follows the rules of universal references. So this function binds to R values and L values. And they might be const and might be not const. And sometimes you need that. When you want to support implicit conversions, you have to use convertible to instead of same as here. This is concepts of C++20. They're looking a little bit like type traits, but type traits with special rules so that you can use them to constrain templates. So here we support implicit conversions. When you even explicit conversions should be allowed, you have to requires constructable from. Please note, just to confuse the Russians, you have to change the order of the parameters here. Another problem we have is, how do you specify a generic R value reference that should only apply to R values? So, because when we say it's a T ampersand ampersand, it can also bind to L values. But we might say, no, it can bind to any type, but it should be should only bind to R values, but any type of R values. So this is what you want to say. Very carefully chosen. I had to discuss it with a couple of people in the standard committee. We came up with different solutions. Yeah, you say, yeah, can be any type, R value to any type, but the thing we get is not an L value reference. Before C++20, you had to use enable if. That's always fun to use enable if. So it looks like that. If you have never heard about enable if, that's good, forget it. And then, I skipped one thing, but I just want to point out another interesting question is, if you declare this not as T ampersand ampersand, you call it T iterator ampersand ampersand. T colon colon iterator ampersand ampersand. What is it? An R value reference or a universal reference? It's an R value reference. You really have to bind directly to a template parameter, not indirectly. And it has to be a local template parameter. It's not if it's a template parameter somewhere over there. Just a local template parameter in the function you declare. We should have used a different syntax for that. And sometimes we have this nice discussion saying, what if we would have taken a different syntax for that? Maybe 3 ampersands. Your reaction is a problem. It would look so funny. Not cool, but everybody would understand the code. And we would not need all these workarounds. I had to think about that when I thought what I told you in the keynote about stood as const and stood ranges as const. Slightly different, slightly the same, but slightly different. Okay. Cool is not a good idea in programming. Precise, unique is a good approach. So, what else? Let's talk about how do we return something. So, we want to return something. Perfectly, of course. When we use auto, that means we return a PR value, a new temporary object. We create the return value. This is, by the way, also the default of lambdas, where you don't declare in a lambda the return type. The return type is auto. So when you have a return statement in a lambda, it creates a new object, or uses what the object you return as your return value. So you might say here, oh, wait a minute, I know how to perfectly return something. It's auto with 2 ampersand, a universal reference. Awesome. Problem solved. Well, that's a reference. A reference to something local. That's never a good idea. It could work. It depends what foo gives you back. If what foo gives you back is something static and you only refer to that, fine. If foo returns you a temporary object, you return a reference to a temporary object. Not a good idea. Compilers will warn you. That's the good news. So for that, there was also a very ugly workaround to deal with that. And for that, in C++14, we introduced decltype auto. Decltype auto says maybe a reference, maybe not. It's a temporary object. If this is a temporary object, so an R value, we return by value. If it's an L value, we return by reference. Roughly speaking. The story is a little bit more complicated, but we have no time to do that. So in generic code, we have a couple of different things when we use auto. Auto, just plain auto, means a new object, a temporary object, or a new object local. Auto with an ampersand means we refer to something as it is, but you cannot bind this to an R value, so to a temporary object or an object marked with move. Const autoreference means, yeah, we bind to everything, but it is const. It became const. Without the const, it is always a reference. Maybe const, maybe not, depending on where we refer to. And decltype auto means if it's a temporary object, it's an object. If it binds to an R value, it's to a reference, it's still a reference. Pretty simple, huh? So, and that is where I come back to what most of you have seen yesterday in the keynote, where we have this saying, where we said, oh, we have views, and the views cache something, and to cache something, they have a problem. That means while you are iterating, you are using them, and you call begin, you modify them, and that means you cannot pass them as a const. So we had the example, if you call print, and the declaration is a const auto reference, that means that you cannot pass this, because this was a view that internally caches begin, and that means while it iterates, or while it starts to iterate, while you call begin, which is the first step when you iterate, it modifies the object, and that is not allowed. And we had to do that, and it could work here, but here we had to say, whatever we pass keeps its state, keeps its category, keeps its type. And that's why we have universal references. Universal reference means take it as it is, as if I would have used a macro. Oh, macro. Yeah, you can universally refer to every expression temporaries and R values as well as L values without making them const. And it's very interesting, I think, when we start again, we should think about that this is our default reference type. By default, a reference is a reference to what it is. And then you do something different to change, to say it's const or whatsoever. But that would be a different programming language. No, I'm not writing in a new language. OK. So universal forwarding references are used for perfect forwarding and universally referring to expressions without making them const. So they deserve both terms, universal reference and forwarding. The only, what I don't like is I always have to explain a forwarding reference is not forwarding unless you call forward for it. It's necessary for generic code taking containers and C++20 views. Please note, there's currently no way to declare a generic function that takes both const and non-const and both containers and views and guarantees by the signature not to modify the elements. It's not possible to do that. An old discussion, which I thought was over, but it's my fault. it's there again. I'm no longer willing to use the term forwarding reference. I think it's a wrong term. Universal reference is the right thing. Looking back, I don't know why because we had that term already, why we created anyway the mess. But we have other terms that are also not precisely correct, but we should be happy if we only have one term for something. Then the next question, when do we teach our universal or forwarding references to beginners? So this is code I could imagine teaching in the first week. Do we want to explain that? And OK. And the last thing is, when should we use it? So still a lot of discussions. But it sounds like more and more in C++ now, with C++20 and 23, of course, also. Universal references or forwarding references are part of our basic vocabulary, even for ordinary programmers. I don't think that's a good thing. Maybe it's helpful, but it is as it is. I can criticize as much as I like. That's C++ now. And we at least have to do the best to teach the rules and the understanding and why we have that. Thank you very much. Are there any questions? I think we have 2 minutes for questions. Yeah, where do we get fresh air? Yes.
Not so much about universal references, more just like a question about like, so when you showed the, okay, so you can construct a string or you can pass a string into a function taking an R value reference to a stud string. Yeah, you can pass a string literal through it and that will implicitly create a temporary stud string and pass that. What stops the same thing happening using a copy constructor? So let's say you've got an L value string and you pass that. What stops a copy constructor being called to produce a temporary object which is then passed as an R value?
The roots we have.
So what?
It's the roots we have, and the roots are there to protect you.
Yeah. But what's so specific? Is there specifically a rule in the language saying that you can't?
The rules you saw.
Yeah.
Though when you saw the slide about this here. These are the rules. These are rules, and they are not in that way, but more or less directly written into the language. And so yes, if you have an R-value reference, it does not bind to a non-const R-value reference. End of discussion. And the reason is, we had a good reason for that. We wanted to help you. Reason in compiler error messages should help you to find bugs. And the reason was, if you have an object that is anyway, you say, well, it started before we had move semantics. So if you have a temporary object, what the hell do you want to modify it if you throw it away right after it? You probably made something wrong.
Yeah, but so what I mean is, like in the case where you're taking an R-value reference, yeah. So you'd be making a temporary if the copy constructor was called, wouldn't you? So that would be like kind of okay. Yeah. So is there a specific rule which says, like in this case, like if you think about it, if you were passing like a string literal, yeah, then that will implicitly create a string, which can be which can be.
Not sure I understand the question correctly, but the copy constructor is just an application. It's a function that follows these rules. So we first have to decide what are the rules to bind.
Yeah. So, but in the case of a string literal, the compiler's smart enough to know it can implicitly convert to a stood string.
Yeah, we could.
Yeah.
We could. Trust me, we have a lot of discussions what we should do with stood.
No, I'm not saying we should. I'm just wondering, what is specifically a rule that says the?
Do we have a better answer? Guy will answer your question.
A string literal.
Do you know what? Do you get the point?
I think what you're saying is that why is it that a string literal will pass to a stood string ref? It's because. Yeah, I can understand. And why will it call the move constructor rather than the copy constructor? So
no, I can understand why that works. What I don't understand is by the same rule. Yeah. Should we take it offline?
Yes.
Yeah, let's do that. Yeah.
You should take it offline in the interest of the people outside online, and they